All right, well, thanks everyone. And again, thanks for the kind invitation. And it's always a pleasure to be here. So we'll continue actually in many ways related to Randy's talk, and much of the work we've been doing actually has been a strong collaboration with Randy, taking now sort of this microscopic look it's on these minerals, which Randy has mentioned. And we'll take a little broader perspective, also connecting with what Mandy spoke about, especially these alkaline type systems, where washing paths actually takes a truly unique position actually in several aspects. So as you see already from the list of participants, it has been really a collaboration, especially on the analytics side. Then from myself, a student from the University of Colorado, Hingdi, who has done together with Joe Smith some of the X-ray crystallography analysis, my student doing bandwidth some of the vibrational spectroscopy. And then this became actually, especially one of the minerals I'll talk about, a very international collaboration doing microprobe analysis in Potsdam by Franziska Bilke, tying into actually one locality you heard earlier from Mandy about the Mount Melosa deposit in Africa. This is actually where one of the minerals, which I will disclose then to you later, was actually after decades of dormancy, then rediscovered and redescribed by Andreas Masanek, who's the curator in Freiberg, specimen and also X-ray expertise brought by Henrik. And then again, this has been now, I would say, a 15-year-long, really true phenomenal collaboration with Randy, doing a lot of the microscopy work and pre-selection of material, which we then analyzed and subsequently published in this subject. So who am I actually? So I'm not actually a mineralogist by training. I actually do optical nanoimaging and ultrafast optics. In fact, work related to what got the Physics Nobel Prize this year, although they kind of skipped me on this round. And so then on weekends, I'm playing mineralogist. I do mineral collecting in Colorado Cascades, also work in China, this was mentioned, work we spoke about last year, and then doing the analytic work. This was actually Bolt Hornet locality for those who know this place. So now let's take a little bit more detailed perspective of what Randy actually spoke about and what makes the golden horn batholiths so unique, that it is actually an intrusion right between sort of a metamorphic suite, this metamorphic core domain, which is largely metamorphic rock separated by a major fault system from this meso domain, which is primarily sedimentary rock. And this is where the golden horn batholiths intruded into upper crust, and it's a per-alkaline calc-alkaline granite system, which then sits elongated here. The North Cascade Highway makes its way through that batholith. Actually, right, as Randy showed, the most interesting zone, and that exploration has then really taken off after the build of the highway. So what is really a alkaline or per-alkaline system, and how would you recognize it more quantitatively? So in the per-alkaline system, you have an excess of alkaline relative to aluminum. This means that primarily the ratio of sodium and potassium exceeds aluminum, and that's what you see on the left side here, where you have this excess of alkaline oxide in relation to aluminum. And the consequence is now that the crystallization of microcline and other feldspar is insufficient to accommodate this. And this is actually why you get this development of these particular type of mineral groups, which has a high alkaline content. And this is now where the agerine, the rhyolite, or starts to become actually rock-forming minerals, and that makes this really exciting. Now, in terms of the characterization of the rock, there is primarily two types, and the washing path generally falls into this category of what's called activated rocks, and they really host these types of very unusual minerals, which are sodium-rich. This is agerine, for example, the calcium, and then we have what's called these high field strength element minerals. These are minerals or elements, chemical elements, which have generally small ion radius and high charge. They cannot readily be accommodated by by primary rock-forming minerals. That includes also zirconium, titanium, and the rare earths. And this is also what you have in the Golden Horn batholiths. So there are a number of such alkaline deposits worldwide, and I think Randy covered mainly covered a number of those and why they are mined also for rare elements or then rare earth. So we don't need to dive further into this. So we'll go right back into Washington Pass and the geography. So again, here is the highway. This is the hairpin turn coming back out, and for those who haven't been there, it's a beautiful area. You have Liberty Bell, which also has prominent mountaineering history for Washington, known beyond the state from the Washington Pass overlook. You have the area of Kangaroo Ridge and the pass as you're looking east. Then there is early Winters Creek and the Willow Creek area, both of which have been actively looked at and successfully found in terms of minerals. I always thought it's kind of funny that now coming from Colorado, Washington Pass is just above 1 mile high, and it's just a little bit higher than Boulder, where I'm coming from. So it seems relatively high in the Cascades, but it's actually not that high in elevation overall. And so the primary contact, which is actually also significant, which runs right along or near this road area, which separates this Black Peak stock, which has nothing to do with the Golden Horn intrusion, except for that there is actually interesting contact, metamorphism, and interactions chemically also, which has been looked at more recently, which helped actually understand the formation and the sourcing of this granite itself. So this is the Golden Horn batholith, and if you want to see actually where this contact is, a good way to look is actually from the overlook, where you see the actual granitic system, which is part of the Golden Horn on the left, and then the Liberty Bell on the right side, and then here is actually where this contact runs through to the Black Peak stock, and you actually see the distinct color of this peak, which is different geologically, different system. So there has been different geologic mapping, every one of which is inaccurate in different ways. So there is actually really need for subsequent work on this. But primarily, you have this arfetzenite granite, which is very characteristically per-alkaline, and then you have what's called abortive granite, which is less alkaline, and as Randy already mentioned, which has then less or fewer of these very characteristic high field strength element minerals, and the rock texture also looks distinctly different. So if you actually look at the rock more closely, then you actually immediately, it jumps out even to every amateur that there is something really different, and this is not the average rock, say, or granite, which say you find in this Snoqualmie batholith. And what really characterizes it is arfetzenite, in this case, so this sodium rich. And then rock forming alkadite, for example. Yeah? And this already actually has sort of an interesting side story to it. And so now looking at a couple of the minerals, again, now there's a little bit more of the chemistry, which were already shown. So the arfetzenite, you see this high sodium content, right? So this mineral can accommodate this excess sodium, and it forms then these beautiful black crystal. What's interesting about it, it's actually named after Johann Arfvedson, who actually was also the discoverer of lithium in 1870. The azurine, I'll actually show this because we had yesterday in one of the rooms a discussion about some, and somebody had actually a very nice specimen. It's a clinopyroxene. It's actually the sodium end member in this azurine augite series. And so some of you may know augite from, it's calcium-rich in the andesite volcanics. And so here you have the sodium end member of it. And this is actually similar. I just put this in this morning because we had looked at a specimen yesterday, which was this typical azurine fibrous texture, and it was just overcoated by a secondary quartz. So for those who were part of the discussion last night. So the golden horn batholith has a growing list, and in this presentation we'll actually add to this long list of minerals which were already described, and in some ways we have a relation of the new work also to some of these type locality minerals, which is sextorite, again, sodium, lithium, zircon, so it accommodates both a very small and very large high field strength element cation, and this is characteristic for many of these systems. And then we have the rare earths and again more of the zirconium bearing minerals. Now, what's sort of interesting, actually, in a little bit an anecdotal way, is actually the alpidite. And if you do see alpidite in this quantity, as we would know now, if you were to go on a systematic hunt for where would I look for potentially a new mineral, that is actually the area where you may actually find something. And ironically, this was actually it's actually in the name. So the name alpidite is actually from the Greek name for hope. And the hope was also in search for mineral deposits, that this indeed is actually in reference when this mineral was named, that you may actually find other potentially interesting minerals. And so here it is. Yeah. So there was, in some way, you could say, this sort of kind of hinted on this potential. Yeah, that there may be something, and then there is indeed still globally the primary sextorite locality, and actually, in fact, due to very impressive effort of a new group of collectors, the whole new generation that has actually been fantastic new material actually been found in recent years in the whole system. So it's actually a great time actually to study and stay here and speaking about the golden horn batholith. Maybe here's a shout out also into the community. This photo, the sketch here is actually the one in the original publication. And I'd be still curious if anybody would know of this whereabout of this specimen. This is a sketch which actually also attests to Bart Cannon's artistic abilities. Yeah, this is actually the hand sketch he made for this article. And so I think the whereabout of the specimen which was sketched here is actually not known. So if anybody would know, this would actually be great for the provenance and the history of the locality to put this information together. So now part of what I will speak about is actually then the heavy rare earths elements. And so and they typically are indicated by where you have typically yttrium, even though yttrium technically is not quite one of the mainly illustrated the rare earth element, but it has the same ion radius, so you can substitute the heavy rare earths in particular, which have smaller ion radius, into this lattice site. And so this also has a beautiful specimen, and the interesting aspect about it is also that Gadoling was actually the discoverer of yttrium oxide, which later then led to the discovery of yttrium as an element by Wöhler. Then there are the light rare earth element minerals, and especially in the secondary and the last stage of crystallization is often these rare earth carbonates, and they are a variety of beautiful crystal habits. They are monogonite, again, sodium, and then rare earth mineral, and then we often have in these systems halite, the halogens, and so this is the fluoride mineral. And so then, as then Randy was collecting, he came across a large number of minerals which you could not simply site identify. And this actually led to my involvement, came in on the analytics side, and then we actually started working on some of the unknowns and going through the catalog, and have some more anecdotes as we go. And so the first work we actually completed was then published in 2016. And this was in some way also, you could say, there is sort of a mineralogical logic in this system. So it was the discovery and the description of this mineral branokite. And so the branokite is actually chemically similar to sogdianite, with the exception that now you substitute this zirconium for tin. And so then if you plot this on this ternary diagram, so here would be the sogdianite, blocked by Jessica. and here would be the brainokite. And so you simply can replace, because of the similar ion radius, the zirconium cation to the tin cation and produce brainokite. What was fascinating about this, and this is now where it's not only adding just another mineral to the list of the golden horn batholith minerals, the main interest is actually what inferences can be made from looking at these minerals, both about the mineralogy of these rare minerals, but also what would they tell us about the evolution of the system of the whole batholith. And so what was fascinating about the brainokite was that it's actually, this is the second locality worldwide reported. The type locality is the Foot Mine in the Kings Mountain on the East Coast. And so that makes it particularly interesting that you have another locality where you can make any comparison to, particularly resolved inconsistencies in the structure. This is a part of the millerite group. And then in this relationship of this structural and chemical comparison to the sogdianite, you can also make an implication that the other element you can substitute for tin would actually be titanium. This would be the mineral beryl-sunskite, and you can actually expect to find that in that system. So it would not surprise you if somewhere in the golden horn there would be beryl-sunskite hanging around. So please keep an eye out for it. Okay. So now this was not a rare earth mineral, so now we'll talk about two specific rare earth minerals then of the subsequent work. So the way you can typically picture this, so typically we prefer nice weather, and then Randy is poking around there, looking for the small cavities he already talked about. And so now on the mineral number 2, Randy at home, working through these little minerals, breaking them up into centimeter-sized chunks. So this is all your homework. Next time you work on the fretzenite granite, and then you look with a loop and a microscope, and you find whatever you can identify, put a red arrow on it, and send it to me. Okay, and we'll see what happens. Okay. Actually, and this actually has to be a shout out, and in some way a commemoration also of Rudy Turner. In all the work, and you will see the uglier photos later after his passing, and these beautiful photos of the work we did together before his passing, that these outstanding photographs from Rudy will be remembered and is in the publication. So here is now one of these unknown minerals which you could not simply site identify. And I have to also say I went through many site unidentified minerals which turned out to be common minerals. We'll get to that later. So this was like a tedious process to find the unknown new minerals. So this was in the talus folder, typical situation. Some peralkaline or fetzenite granite. You know, this arfetzenite, anite in quartz, and small cavity, unknown mineral, a couple millimeter, and associated a little bit of the other unusuals, wolfenite, zircon, pyrophore in the system. So now we'll analyze this. And now here comes something totally funny. I'll take this under. It turns out to be selenite. So selenite is an yttrium-rich mineral. And so when I put in the microprobe, you see characteristically actually this yttrium peak in the silicon. And I actually thought I made a mistake, because what I typically do is I'll put a bunch of these little unknowns onto a carbon tab, put it in the electron microscope, and I have just the day before looked at selenite from Colorado. And so I actually thought initially I confused something. I mixed up some sample number or something. That why am I seeing selenite again? Because we were just analyzing this in the Pikes Peak batholiths. I'll talk a little about Colorado more tomorrow. And why were we interested in selenite? Because actually, even in the 60s, this particular pegmatite in Colorado was actually the second world occurrence or known of selenite. So it was only as analytic techniques evolved, people have discovered its presence more. And so this is a totally different geologic setting. It's an A-type, not alkaline type granite. It's a pegmatite occurrence. And so, but then checking, of course, and I realized, well, indeed, it was pure coincidence. It was a matter of days of these two convergent projects. Suddenly I'm looking at selenite and have two different localities I can make a comparison and then inference on the different evolution of these different fluids. So a little background now for the non-experts. How do you actually analyze those types of rocks? You look use an electron microscope, costs you upwards of $500,000. What it does is it has an electron beam. Not only produces this image, but it also, in a particular electron energy, it ionizes the atoms. And when that happens, electrons from a higher lying shell of these in the atomic structure can then reoccupy this hole which is generated by the initial electron emission. And this emits characteristic X-rays of a particular photon energy, which is characteristic for the chemical element. Yeah, and then you have two types of techniques. One is where you then wavelengths disperse these X-ray photons and then calibrate the instrument and can get quantitative information of the presence of these specific elements and how abundant they are. So this is how you do electron microprobe analysis. So here are elemental maps of these phthalate crystals. They are heavily zoned. What's quite fascinating that locally there is a very high abundance of ytterbium. And this is because this crystal structure of phthalate is such that it likes to incorporate the small cation size and likes to incorporate the heavy rare earth elements which have small ion radius. And so this was already a surprise that we have this very high enrichment in ytterbium. And so then when we compare now the rare earth distribution in the different phthalate, these different geochemical environments, then plot their relative abundance, and you already see qualitatively there's a big difference. Whereas in the pegmatite system from the South Platte pegmatite, you have this continuous enrichment of the heavy rare earth elements substituting into this yttrium side. Whereas in the golden horn, you do have this increase up to a certain element number, and then you have this depletion of the very heavy rare earth elements. And so what this allows you actually to infer is that from this depletion of the heavy rare earth, that this is actually of hydrothermal origin, as it's not unusual for these mitolytic cavities of the golden horn, and especially a late stage where rare earths got remobilized and then crystallized, then the phthalate is late. This continuous enrichment in the white cloud actually indicates that we have actually a primary magmatic process. And so this is how, if you have an abundance, and this is typical for these pegmatites, you have an abundance of the rare earths, and so then the crystal, more in thermal equilibrium, tries to incorporate its optimal number of rare earths, and therefore when you get this continuous enrichment of the heavy rare earths. But there's also actually secondary processes and multiple generations of that in that system. So then, of course, for full verification of the type of mineral is, of course, you look at the X-ray diffraction. So you look at the periodic lattice. Now you diffract X-rays, so that confuse this X-ray spectroscopy into microprobe. But you diffract the X-ray beam at the periodic lattice, and then from analyzing, and this is for the older of you who remember the days where you have to flip through books and compare X-ray pattern and all this. So I'm glad to be a late born and not having to deal with this. And now you use actually machine learning algorithms and artificial intelligence systems, which can actually get you from these large data sets. It's really a data science challenge now, but that actually accelerated and made X-ray crystallography now real fun, okay, for the computer piece. So now what was interesting about the phthalate, and this was also new information about this class of minerals, is actually what we call now internal fractionation. So we have on even nominally this yttrium site in the crystal structure, but there are three crystallographic different sites, and they do have slightly different coordination then with the oxygens and the silicon, and this gives you then different sizes of these of the lattice site, and then it actually turns out that of these different sites we have actually site fractionation, site ordering. So it's a preferential occupation of one site over another. So this was an interesting outcome of that, and that was then published in 2018. Actually, the work now also again this collaboration here of the different contributors who did X-ray and microprobe and piecing this all together. So now it took a longer time for the next project, and we still haven't, or we actually just wrapping this up. And I'll tell you now why this was so hard. Now, so again, Randy looks at a microscope, story starts the same way over, right? So here's the thing. So what are we looking at? Here's what we're looking at. And now you see already distinctly, I don't want to diminish my friend Mike Gobler for these microminerals. It also has to do that these are not as pretty as the phthalate, but we are actually in need of somebody who would take nice microphotograph images. So there are these crystals. And so this actually comes from this sogdianite pegmatite, which is a block of rock, like most, as Randy showed. And so this is a unknown here now, so it's a millimeter long. It's opaque, has a square cross section, but actually many of these crystals turn out to be partially or completely altered. And you're happy to come up here later. We have two specimens here we can take a look at. You can also take a look at the granite. So now again, we repeat the story. I put it in an electron microscope, and this is the first thing I'll see. So there is actually what still seemed reasonably crystalline to under the optical microscope turns out to be actually a pseudomorph essentially. So it's altered and replaced by a whole sea of elements. In particular, there's a lot of thorium uranium enrichment. There is all the rare earths in there, and there's phosphates in there. So it's a highly altered system. So fortunately, then here's a better candidate, and analyzing that now, this becomes a lot cleaner. So it turns out to be a calcium yttrium silicate. So we have a calcium yttrium silicate. Okay. So what do you do now? Now we actually take a look back into Rusbach's thesis. What calcium yttrium silicates he has, and he actually describes, as he speaks about, in fact, this sogdianite pegmatite boulder, this small pegmatite, that there is cyanide and then there's an unidentified calcium yttrium silicate where he provides analytical values. So we thought we were done. Okay, we got that. Now it should be easy now, right? With the modern tools to get this all squared away. Well, he speaks about white square prismatic crystals, so this matches our description. He thought it's helenite, but he also acknowledges that there was not a good match on his X-ray powder diffraction, which is not surprising. But we kind of thought, well, we were getting really close and really fast. It should be wrapping this up quickly. Now it turns out that as I looked at more material, most of the time I'm actually running the kinesite. Now kinesite is actually very similar to what it actually will turn out to be. So this is a calcium yttrium silicate with carbonate and water. Beautiful crystals. Of course, Rudy Turner's photos. So then we do X-ray diffraction. I thought this will settle it now for good. And so we take different samples from Washington Pass, and we look at the lattice structure, and we get in good agreement with a mineral which was described in 1974, and then later with the structure in 78, which would be caesiosite. Yeah, we'll talk more about this in a minute, but there is something very confusing. And then while everything agrees, the unit cell dimensions, the space group is different. So we have actually, instead of this PNMN group, we actually have a center symmetric group. You know, we were wondering about this and said, well, okay, so maybe this historic analysis was wrong, because you see now what the modern techniques allow, the number of reflections you measured and how many unique reflections. This is now in the tens of thousands, whereas they only had hundreds of few thousand, which they could properly analyze in the 70s. And so now let's look a little bit at caesiosite. So where did this come from? So the type locality of this material is actually a very obscure locality. It's a feldspar quarry near Ottawa, the Evan Lou mine. This was mined actually for feldspar briefly in the 50s. And it is actually type locality of multiple minerals because it has a very high yttrium content. And so this caesiosite was these little fibrous needles there. It was first recognized as potentially a new mineral in 69. And then Hogarth described it in 72. And then the crystal structure was resolved in 74. And so it's easy to remember now because I like minerals which are named by the chemistry. And that's why where this name comes from. Caesiosite. So calcium, yttrium, silicon, and then we have carbonate and water. Yeah, so perfect, right? So kinesite now is very similar, has different crystal structure, and all you need to do is to get from caesiosite to kinesite is you actually replace two carbonates into an oxidant. That's the only difference, right? So we have O10, now we have O12, so two of the carbonates, so it's the into one, right? The keep charge balance, carbonate is 2 times negative. So you do that, the crystal structure is different. You can accommodate less water, but the kinesite was in the constant in the back of our mind because also they are visually similar, and many of the specimens we looked at was actually kindesite. So it was really hard to separate out calcite. So here are other type locality minerals, all yttrium minerals out of this interesting deposit, yet confusing. The crystal structure is fairly complex, and it has these two distinct sites. There's an yttrium site, there's a calcium site, and then what's hanging out all around, which holds this together, right? You have these very close in vicinity, strong charged cations, and you have water and carbonates. The water gives it sort of space, and the carbonate are structurally important to hold it together. So it's a complicated structure, and that was also why the original publication of this was quite an elaborate discussion. There was subsequent work by Hawthorne, who has then managed to get a little better visual picture of that you have sort of these ribbons of calcium and yttrium polyhedra, which hold the structure together. So it's actually a really interesting mineral. So when has anybody seen cacheosite elsewhere out of this locality from Ottawa? So 20 plus years later, Mount Melosa came onto the mineral world and had flooded the market with phenomenal specimens of azurine, barrelite, amazing zircons. So things you kind of see in the parasite or in other carbonates when you see it washing past its micros, you have its macros from Mount Melosa. And so this is a per-article granite in Africa. So what you don't see here is an article from Andreas Massanek from 1999, where we get the citation down there. You can imagine the rest. You would see on this picture, if this would slide correctly, a beautiful specimen of macro cacheosite of a centimeter long, which was given to the museum in Freiburg out of this pool of material from Malawi, was on display as a zeolite. It's a white, nice looking crystal, and like we saw earlier today. And then it was Andreas' foresight to look at this looks kind of strange for a zeolite, even though it's a white mineral. So he put it in the microprobe and recognized it was actually cacheosite. So the world's largest specimen of cacheosite came from Mount Melosa, were potentially in different mineral collections, potentially still undiagnosed today. So anyway, so then we need a reference material from this locality. So for those who know Uli Baumann, who are interested in African minerals, he had pallets of this material shipped to Collector's Edge, and I was mining through pallets, so not outdoors, now indoors mining in the Collector's Edge warehouse for going through hundreds of specimens from material from Mount Melosa, looking for cacheosite because now I need a reference material, right? And there it is, I found it. So these are cacheosite crystals on a ugly azurine, and they are beautiful. So they are clear crystals and perfect analytic material. So let's check that out. We do the X-ray crystallography, and again, we get this weird different space group. Now, matching the washing path space group, but is again different from the space group from the Evan-Lu mine. So you keep scratching our head. And again, we sort of hate this project. We should long be done about this. Why are we dealing with these companies? So now it gets worse. So now I need to find, of course, Evan-Lu type material. This is hard. This mine was abandoned. Nobody cared much about this locality anymore. You go in the mineral market, you go to collectors, to museums, and you look for this. It's crusty stuff. This quartz. You look for more crusty stuff. That's what you're looking for. You're looking for these different. Nikisher sent me. Everybody sent me material. I kept analyzing. Now at least we got an yttrium mineral, but it's not what we need. So fortunately, then actually again. Accidentally reaching out to Henrik Fries, and we collaborated with Port Oslo. Their museum has cacheosite from the type locality, which looks acceptably analyzable. And then also Sebastian Miller and Marburg gave the material. And indeed, now we got it. Okay, so thank God. We got cacheosite from the type locality to finally reanalyze and see what happens. This is still a hard project. These crystals are, as you saw in this picture, these are very fine needles. And this is also the reason why they had a hard time in the 70s to do proper X-ray crystallography. Okay, so now we actually use a synchrotron light source. So instead of a tabletop X-ray, of course, you use coherent X-ray radiation from a synchrotron, where you then, this micrometer precision, can actually do X-ray crystallography on single crystal. And even that was hard because these crystals actually, turns out, probably because they grew fast, they are twin. Here you see actually, well, not on the resolution of the screen, but there's peak splitting. And sorting through all this out, we actually came to the conclusion that indeed the type material is C-centered orthorhombic. So it does have a different space group than the Washington Pass and Mount Pelosi material, and it has actually distorted carbonate cations in the lattice structure. And so what's also confusing now, though, if you do the side refinement, this means you can take the X-ray signal to determine how many electrons are sitting on each of the lattice sites. And if you do this, it actually turns out that on the calcium and the yttrium side, there's about equal electron density. Now, this is very strange. So there is a calcium site which should have much fewer electrons than the yttrium site. That's in the ideal crystal structure. So now we dive deeper and look at and actually project from the X-ray data an expected chemical composition, which would indicate actually about a oxide weight percent of about 14 to 8% based on the expected charge density. Here's these differences in charge density. I know I'm getting very technical before lunch, right? I'm probably losing half of you already. So this different electron density actually would tell you that there would be, this is the calcium is much lighter, the yttrium much heavier. This is what we would expect for the Mount Pelosi and Washington material. Now, yet, comparing this with the type analysis, now we are seeing indeed that on the type material, there's a much lower calcium content. And so what this tells us now, if we now do the full crystal chemical analysis in the microprobe of the comparison of all the different localities, so we do have the Mount Pelosi, Golden Horn, the reanalysis of the Evan-Lu, and then in comparison to the literature. We actually have phenomenal agreement between the type analysis from the 70s to the new analysis. And what we see, though, is that the confusing thing about the type material is that you have an axis. You already have the yttrium site would already be completely full with yttrium. Now, if you add the other rare earth elements, and all of which are higher than in the Golden Horn and Mount Pelosi, where we have a lower yttrium content, you actually have an excess of the rare earths for the yttrium site. And you have a deficiency of the calcium site. And so what this tells you actually is that we need to write the formula that we do have now mixing of rare earths onto the calcium site. And this gives rise to an equal electron density of these two sites and is then responsible for this different structural disorder and the lower symmetry. So we got it. This actually is just pieced together about a week or two ago. And so we're just writing up the manuscript. So now let me summarize this. So here is what we learned about acacia site. Now again, new species for Washington Pass, and it could be added to the MinNet database. And so we compare now again the Golden Horn to the Pelosi and Evan-Lu, so type locality plus this, what we would now propose to actually become a co-type locality for this acacia site Mount Pelosi because of the higher symmetry. And so we have this structural disorder which lowered the symmetry on the type material, probably because it was grown fairly rapidly, and this is why you have this different crystal habit, this more fibrous growth, whereas here you have these nice orthorhombic crystal texture. And then the phthalenite, I just want to summarize again what we learned from this. So also, in the end, yttrium silicate mineral, and then comparing that Golden Horn with the pegmatites from Colorado, you actually make inferences on the different petrogenic evolution, both in the pegmatite as well as in the Golden Horn. And then again, we learned both about the mineralogy itself, about the site order on these different lattice sites, but also again highlighting the fact that the Golden Horn system also then for the acacia site is actually myelolytic hydrothermal. Right, so with that, I'd like to thank everyone in the audience. I'd like to thank a lot of people who have contributed to this effort in one capacity or another over this period of the research. And let me now make just one quick shout out, and then we'll take questions. We'll get a preview for tomorrow about analyzed or not, and maybe incorrectly so. I will speak about Colorado serite. And the reason why I will highlight this also is because I did bring specimen. This is a globally unique rare earth occurrence where we've done research over many years. it led to and was evolved as also this model about immiscible fluids, which gives rise to rare earth formation. So we also have specimen for sale. The proceeds go to the club. There will be one. There are some in the silent auction. There will be one in the auction tonight. And again, I just brought these specimens. All proceeds go to the Friends of Mineralogy in the Pacific Northwest section. So I really hope that you bid heavily on this material. Yeah. Yes. And then there will be now one more surprise. You probably know much about these minerals and Thea, and the photo here beautiful from Joe. She has in the room. So it's this Hastings site. And so there is a long story and a great story. I have a couple slides tomorrow. This is not rare earths, but it's something which I think the Northwest community has been fascinated about. Going back into 1936, this material was recognized to exist in these Wenatchee andesites, and there were many suggestions made what this could possibly be. Yeah, from whatever hornblende, ongite, this, and Bart was confused. And it's none of this. Okay. And we'll tell more about this tomorrow. Okay, so with that, I'll thank everyone, and I'm happy to take some questions. Maybe with this slide up here.
I was interested in the original Evans-Liu analysis, right? You were able to confirm that space group.
Yeah.
You had to use, because it was secular, you had to use the sacred line to get the structure. How did they do that originally?
So they were fortunate to, from the description in their publication, that they must have had larger, or when they grow in this acicular fashion, they have somewhat larger crystals. But they also, and I simplified this a little bit, that this they were also not so certain about that. So there is actually a bit of discussion about how they go through the analysis of their space group assignment, and they were baffling around a little bit, but then kind of settled on that. But it wouldn't hold up standards today. But again, it is largely an inconsequential question, right? It's really some of the internal the unit cell matches. It's just about how, by changing especially this carbonate ion orientation, right, and you're losing some of the symmetry operations. Yeah.
Okay, we have our next speaker will be our final virtual speaker, Glenn Waychuna, speaking on rare earth element activators for luminescence, and that will be at 2 o'clock. So you're on lunch break. We'll see you back in this room at 2 o'clock.